Hey there, everybody. We're going to get rolling here. Hope your week's been going well. Feels like it's been a quick one for me. I think it's gone well. Had St. Patrick's Day this week, always one of my favorite holidays. Tomorrow morning, first thing is my first COVID vaccine shot. So I think it's a good week, both St. Patrick's Day and a first dose of the vaccine. I'm not going to complain at all about that. Our plan this evening, we're going to spend the first part of class looking at some ideas within chapter 8, and then the second portion begin to move on to some ideas within chapter 9. I've got some polls along the way that I think are targeted on important ideas. So, I mean, I hope you pay attention every class, but in this one, please pay attention to our story as we go through, because I think then the polls are going to be some good applications for you along the way. So we saw within chapter 8, we briefly looked at the idea of ionic bonding, a couple of skills that we wanted to be familiar with there. We need to be able to do rankings involving lattice energy, and we need to be able to understand aspects of the Born-Haber cycle. Those would be our objectives in 8.2. When we're looking for the rest of the chapter, though, it's all about Lewis structures. It's all about being able to draw Lewis structures, interpret them. And as I think you saw with the pre-class video, that's a key skill that we need at the start of chapter 9 as well. And in fact, in all of chapter 9, Lewis structures are going to be important. So tonight we're going to see a little bit more, revisit what does it mean to draw Lewis structures, and then begin to look at a few different applications. So let me send you this initial polling question. I'm curious. So people were doing an outstanding job for the 2 different assignments that are listed there, one from chapter 8, one from chapter 9. You're really blowing me away with how great you're doing, commenting on your own understanding, participating and responding to each other. When I look at what you're up to there when you first started the program and what you're doing now, I'm just so impressed with people's contributions. Now, I have 2 different optional ones that were listed there. One that was looking at some ideas from chapter 7, and then another that's ideas from chapters 7 and 8. And in both of these, I'm trying to give sort of exam quality questions for us to think about and discuss. So in these optional ones, I try to share and explain questions from both 7 and 8 that I think are really relevant for the upcoming test. Now, I'm just curious within this. There's no right answer. I want you to choose what choice best describes your view for optional assignments like this. I'm not aware of this resource. I don't need it. I know it would help me, but I really don't have time for anything optional. I think I'll look at the questions. I might try some, but I'm not really going to participate in perusal. I'll answer these questions and discuss my work in perusal. Or finally, I'm not really ready to think deeply about these. I might use it closer to the time that the exam's coming around. So I'm just curious within this one. So we got 6 different choices. What would you say best describes your view? Okay, take about 10 more seconds for me, please. I'm just curious within this one, the share a results with you all. I know I understand all the choices. Okay, I mean, there's no right answer here, right, wrong answer. If you are able to participate within the space, and you find it beneficial to discuss with me your work in there, I'll be happy to. Okay, doesn't hurt my feelings whether you work on it or not. But if you find it to be a useful resource, I'm happy that you can use it. The spot where we're going to pick up here in chapter 8 then. We looked last time at drawing Lewis structures, the idea of the octet rule and formal charge, and how this would be useful when we're looking at molecules. We certainly need to be able to draw Lewis structures. And then going on and being able to calculate aspects like the formal charge and use that to identify the most optimal Lewis structure, that's a skill that we need to have. New idea is going to be looking at resonance structures. So the big idea within this is that when we draw the Lewis structures, there's times when they may be combined. A single Lewis structure won't be sufficient. And with resonance structures, we're considering when we have more than one valid Lewis structure. So what we want to be able to do is identify when this is going to occur, and then think about, well, what does that then mean to the structure of the molecule? So we want to know, when does it happen, and then what does it do? In the last part, when we're looking at exceptions to the octet rule, we're going to find that the octet rule isn't applicable for every atom. Last time I mentioned a few atoms where we're going to see that it works almost all the time. And then at 8.7, we're going to begin to look at some examples where that's not appropriate. So this was our scheme that we had last time, our procedure if we wanted to go through and draw the Lewis structure, beginning with writing the total number of valence electrons and then going all the way down and trying to construct octets. And when we evaluate it, a good initial question was, well, do we have octets? And if not, it might be the case because the octet rule is not going to be applicable. We'll talk about that tonight. We want to be able to assign formal charges. And then another thing we ask when we hit a Lewis structure, we can ask is, well, are resonance structures possible? And what would that mean? So resonance structures, that's a new idea for us. Let me illustrate that by looking at the structure for ozone, which is O3. So within this one, I'm going to first begin by adding up the total number of valence electrons. Each oxygen has 6, so that gets me to 18. I draw just single bonds initially. I'm going to complete octets around the outside. That gets me to a total of 16 electrons. I need 18 though, so I'll put 2 more there on the central atom. Now, if I look at these, I've got octets around the outside, but not on the central atom. So how might we be able to make octets? Well, last time, if we had octets around the outside, but not in the center, we shifted in lone pairs to begin to make double bonds or maybe even triple bonds. So if we were to decide to shift in, what side are you going to shift in from? Are you going to shift in electrons that are found on the left, on the right, or does it not matter? You could shift them in from the left and make a double bond, or maybe you want it to go the other way. You could shift them in from the right and make a double bond. My point is, both of those are equivalent. One was just shifting from the left side, one was shifting from the right side. We kept the atoms where they were. We had 2 different ways that we could shift the electrons and end up with the same result. Those are the example of 2 resonance structures. 2 different ways that we could draw ozone that are equivalent to each other. So when I'm looking at this resonance structure, what I'm doing, I'm keeping the atoms in the same place in my Lewis structure, but I'm finding that there are 2 equivalent ways that I could arrange the electrons. One of them just has a double bond on the left, one of them has a double bond on the right. Now, why might this be relevant? This is a Lewis structure that we could have for ozone. Below that is a representation of the actual structural features in ozone. By using a technique like X-ray diffraction, you can determine what the actual bond angles and stuff would be within this molecule. Pretty cool technique. Now we have 2 different possible Lewis structures though. How do we end up having those used to describe what the actual structure is? The book gives this analogy. It's as if you have 2 different colors of paint, blue and yellow. You pour them together and now you end up with something new, green. After you pour it together, you no longer have blue and yellow. You have a combination of those. And they're trying to say that's what happens with resonance. When you have 2 equivalent Lewis structures, you do not have a double bond and a single bond. You have a combination of those. So that would affect properties like, let's say, the bond order. What is the bond order for each of the oxygen-oxygen bonds in something like ozone? It's not going to be 2. It's not going to be 1. It's going to be somewhere in between. And that somewhere in between, I can just average it. If I average a value of 2 and 1, I get a value of 1.5. That would be my description for the bond order here in ozone. I'm doing an averaging of a double and a single. One way you could think about that, that would be a total of 3 bonds cut in half, 1.5. That would be my description for my bond order. And if we look at the structure here, it looks like they're equivalent. They're the same length on either side right here. This idea of resonance, of describing the structure, we do not have a single bond and a double bond. We have something in between those when we combine them with our resonance structures. That idea right there, I'm going to put it in red because right there, just that idea of how we have a combination of the Lewis structures giving us something new. I've seen that many times as an exam question all on its own. And when I say many times as an exam question, this is a very typical format for it. So this would be how I'd expect it on a test. It says, consider this Lewis structure for ozone. So it gives us a Lewis structure. What best describes the bonding in this molecule? Would it be a double bond and a single bond that remain fixed? A double bond and a single bond that rapidly move back and forth? Or 2 equivalent bonds? Let me send you that as a polling question. Very typical exam format here. So as this is coming in, we've got really 2 main perspectives amongst the students. Take about 5 more seconds. Okay, so here's the results within this. So some folks, about 10%, are saying it looks like a double bond and a single bond. And then the rest of the class is trying to make sense of, well, how do I begin to think about this involving resonance? The way that I want us to think about this one, well, first of all, when I look at that, I am going to first identify this one as resonance is possible, because I could keep I could keep the atoms in their same spot and come up with an equivalent structure where the double bond was on the right instead of on the left. The way that I want us to think about that is we are going to end up with 2 equivalent bonds. It's sort of like our picture of that in that analogy with the paint. After you have both of those 2 different colors that you combine, you end up with a new color. It's not like it's going back and forth somehow with these contributing colors. You're not going back and forth with a double bond and a single bond and somehow smearing them out. You no longer have a double bond and a single bond. You've got something that I'm going to call a bond order of 1.5. It's somewhere in between a double bond and a single bond. And that's what's consistent then with the actual experimental data. So I want us to think about this resonance as it leads to a new set of equivalent structures. It's not a rapid going back and forth. Let's look at another example where resonance is relevant. So let's look at how we would construct a Lewis structure here for nitrate. So our first step, let's add up and get the total number of electrons. I added 1 because it was an anion. So I have a total of 24 valence electrons, and I would draw nitrogen. It's my center atom. It's least electronegative out of those. Next step, add electrons to the outside to complete octets. This is an anion, so I put it in brackets. This picture right here now has all 24 electrons. If I look at nitrogen, though, nitrogen's not an octet. So we can now switch one of the lone pairs, move it in, and make it an octet. So you got your choice. Are you going to switch your lone pair from the left, from the right, or from the top? You got three different ways you can do it. You got three different ways, and that leads to three different resonance structures. All of these are equivalent. We've just shifted where the lone pairs became a double bond. So I think within our resonance structure, now we have an averaging of all three of these structures together. These would be the resonance structures appropriate for nitrate. So if I look at these three examples right here, take a second, look at one. Is the octet rule applicable? Is it being followed by both nitrogen and oxygen? Is it being followed by all of the atoms? I think it is, okay? I think I see octets however I look for nitrogen, oxygen, either of the oxygen environments. Take a second now, see if you can calculate what is the formal charge for nitrogen. Nitrogen has a double bond, a single bond, and a single bond with no lone pairs on it. I'm going to send that to you as a polling question. Take a second, what is the formal charge for nitrogen? See if you can recall how we did that calculation and see if you can calculate that. I'll send you a polling question on that. So take your time with it, but then what would you say is the formal charge for nitrogen? Formal charge is an important thing to be able to calculate. And I say that as far as if you're taking a multiple choice test, because we can't have you draw and submit what your Lewis structure is, but we can have you draw and then we can ask you something about it. And one thing we can ask is, tell me about the formal charge. Take about 5 more seconds. Formal charge, that's going to be a really good skill to be able to do promptly. So as far as this one, I'm seeing a dominant perspective that it looks like it's +1 for the most part. I agree with that. If I look within the calculation, remember what we did? We took the number of valence electrons. So for nitrogen, it's 5, 1, 2, 3, 4, 5, minus half of those that were being found in bonds. There's no lone pairs. It ends up being +1. In fact, I show what it would be for the other atoms like this one on the left here. The oxygen with a double bond has a formal charge of 0. The oxygens with single bonds are -1 and -1. And so I'm always reassured when it adds up to the overall charge of this anion. Now, if we look within that one, what do you think the bond order would be for a nitrogen-oxygen bond in nitrate? I'm going to send you a polling question on that. What do you think the bond order is for this nitrogen-oxygen bond in nitrate? And your responses for this are really helping me. Take about 10 more seconds. your response is really helping me on this one because it tells me, okay, I got to explain this more. We're all over the map on this one. Okay, we probably couldn't have more of a distribution on this. So let me tell you my strategy. Let me try to explain a little bit more clearly how I get the bond order. So my first thought within here is I see different resonance structures are possible. So I'm going to have an averaging of the bond. I am not going to have a double bond, a single bond, and a single bond. Due to the resonance, I'm going to have an averaging of those environments. So the way that I calculate then what would be the resulting bond order, this is how I think about it. This nitrogen in the center, it has 3 different directions that the bonds are going in. I see a total of 4 bonds. 1, 2, 3, 4. I see a total of 4 bonds that are being split up in 3 directions. That means they're each a 4/3 bond. Total number of 4 bonds being split up in 3 directions means each of those is a 4/3. If you add up 4/3 plus 4/3 plus 4/3, you get the total number of 4 bonds that would be present. That's how I would come up with the bond order for that. So in order to come up with the bond order when I have resonance, and it's something that we can practice again, in order to do that, I'm going to get the total number of bonds and then divide it by the different directions that they're being directed. We'll practice that again later this evening. So in this case, I would predict all of the bond distances for nitrogen, oxygen, all those bonds are going to be identical. They're going to have properties somewhere between a single and a double bond. 4/3 is more than 1, it's less than 2, it's somewhere in between. That's what I predict is going to happen. So what I've been spending a little bit of time here in 8.6, again, 2 skills with resonance. When is resonance applicable? When do I have equivalent Lewis structures? And then how does that begin to affect the properties of the molecule? Now, let's move on to examples where we do not have the octet rule be applicable. So I give 4 different formulas here. So polling question for you. I talked last time about elements where I really think we're going to have the octet rule be applicable. Based on that list right there, I want you to select all, okay? Which of these elements that I have listed would you say, okay, it's going to adhere to the octet rule? These are the ones that are shown within those molecules. So as these are coming in, I was thinking to myself last time, okay, hydrogen, that's always going to form just a single bond. Then we had another set of elements that we said, okay, this is always going to follow the octet rule if it can. That's what I'm asking about here. Which ones was that applicable for? So as far as this one, the consensus is coming in, I'm seeing the strongest consensus that, okay, fluorine would be an example that it would form octets, as would nitrogen, as would oxygen. The other ones are down from there. I'm going to agree with that assessment. I think that this is my group that I'm going to have octets for pretty much all the time. Carbon, nitrogen, oxygen, and fluorine. That's my core group that I'm going to say, you know, when I draw my Lewis structure, I want octets for sure for those. And I'm going to be more willing to compromise for other ones, but that's my core group. So when we're thinking about things that might not form octets, it could be anything beyond that particular group right there. So let's look at a few examples. So in BF3, this would be the molecule for BF3. I'm making octets for the fluorine, but boron there, it only has 3 bonds, and there's no lone pairs present on that. This would be an example of we don't have an octet because we only have 2, 4, 6 around the boron instead of reaching 8. Boron is a great example of one that does not reach an octet. How about in NO2? Now in NO2, first question, well, how many valence electrons does it have? When I do that particular molecule, I see nitrogen has 1, 2, 3, 4, 5. Each carbon has 6. That adds up to be an odd number. You can never reach multiples of 8 when you have an odd number. We don't have that many molecules that have an odd number of electrons. NO2 is an example. So this would be another reason you wouldn't have octets. If you have an odd number of electrons in the molecule, you can't get valence electrons, you can't get to octets. So that's why you see within this one, it's got that single electron being found there, or a single electron being found there. Now with both of those, I worked through the formal charges, and this is what you see. So take a second, look at those. Based on the formal charges, which of those do you think is more likely? Think it's going to be the one where your zeros across the board. So this would be, I think, the best Lewis structure you could write for NO2. But it's in a case where you're not making octets because it has an odd number of valence electrons. Now, this one right here, SF6, this is going to be, I'd say, a pretty important example for us. This would be my Lewis structure for that. I'm making octets for all of the fluorine atoms because that's an atom that I'm going to make octets for. But notice when I do that, that sulfur now, it is going beyond an octet. But based on its formal charge, it's fine. And when I say that, sulfur has 6 valence electrons. After I count for its formal charge, 6 minus 0, it's going to be formal charge of 0. In fact, all of these are formal charges of 0. This would be a case where I like this structure because all of the formal charges are 0, even though it meant that it was not consistent with the octet rule. So you might ask, well, when do you have it not consistent with the octet rule? When you have larger central atoms, they often go beyond an octet. And when I say larger, anything below that set of carbon, nitrogen, oxygen, fluorine. Sulfur exceeds an octet quite frequently. Phosphorus can, chlorine can. As long as you have these larger atoms from the 3rd row and down, they will often exceed the octet rule. Another example here would be xenon tetrafluoride. This would be the Lewis structure for that. Fluorines, again, are all consistent with the octet rule. When I say I'm not making this up, this is an actual molecule. Xenon has 8 valence electrons, and it will form bonds with something that's very electronegative like fluorine. I get xenon having 8 valence electrons because I'm just counting over from the left-hand side. I'm not counting my d electrons in that. If we look within this with xenon, I see 1, 2, 3, 4, 5, 6, 7, 8. Formal charge is 0 for it. Okay. This would be another example, though, where we have a larger central atom and it exceeds an octet. That idea of exceeding an octet, they call that hypervalent. It's going beyond just the octet rule of 8 electrons. So we sort of then have, coming back to our guidelines, what do we say is a better rule? Is it the octet rule or is it the formal charge? I am going to use the octet rule back for carbon, nitrogen, oxygen, and fluorine. But for these larger central atoms, like sulfur or xenon, I'm going to be fine if I exceed the octet rule, and the formal charge would be useful for me. In boron, that's our classic example of we don't reach octets with that. So these are all in the section then of what does it mean to not be consistent with the octet rule. Next set of ideas here, this is related to one that was in the pre-class video that people were doing a really good job on. The idea that we had different representations for bonds, but they all came back to this idea of having electron density between the 2 nuclei, being attracted to protons in both, and being able to then hold those atoms together to form a bond. And that we could then describe that bond in different ways. So here was some data that was shared in terms of the bond length and the bond enthalpy values. We want to connect things like bond enthalpy and bond length. So within this one, this is sort of a summary from what we saw within that pre-class video. we had different bonds, single bond, double bond, triple bond, where we saw the length was changing. We saw as the bond order went up, the atoms were getting closer together. We saw as the atoms got closer together, it was forming a stronger bond that was represented by a larger bond enthalpy. So when I think of a strong bond, I'm thinking of all of these different ways of describing it. A strong bond means the atoms are closer together, it's a shorter bond. There's a stronger attraction there. It has a very high bond enthalpy. It would take a lot of energy to break the bond. Bond association energy, that's another term you might see that is really the same kind of idea as bond enthalpy, but it's just thinking about the breaking part, the endothermic breaking of the bond. As they've come together, I think they've gone to a lower and lower potential energy. And I'd say this corresponds to a higher bond order. All of these ideas are what I'm thinking when I'm thinking about what a strong bond would be. So we might ask, well, how does resonance fit into this picture right here? Let me show you on that. So really typical exam question, something like this. Compare the carbon-oxygen bonds in methanol, carbon dioxide, and carbonate. So in order to compare the bonds, I first want to be able to draw the Lewis structures for those. I think methanol would be one that we could quickly draw. I think carbon dioxide is one that we could quickly draw. And when I say we could quickly draw it, it comes back to within the methanol, hydrogen's only going to form one bond. Notice how the formula is giving us ideas about the connectivity. CH3, so a carbon with 3 hydrogens around it. And then it's saying there's an OH group attached to that. And by adding in the remaining valence electrons, we get the 2 sets of lone pairs. Carbon dioxide, I think that's one we've seen quite often too. For carbonate, let's go through the plan of being able to draw that. So I'm first of all going to get the total number of valence electrons. Carbon has 4, oxygen has 6, and I have 3 of those, and I'm going to add 2 on because it's a 2- anion. So I get a total of 24 valence electrons. In my sketch, I'm going to put carbon in the center, and I'll draw single bonds throughout. Next step in the process, let's put octets around all on the outside. I'm putting brackets around it, and it's 2-. So if I count them up right now, I have 24 valence electrons, and that's the number that I started with. That's the total I want. So I like my total number of valence electrons. But what I don't like about this is I don't have an octet on that carbon. So how might we make an octet? I think we could switch in a lone pair, and it's your choice. Do you want to switch the lone pair in from the left, from the right, or from the top? Now, as soon as I say it's your choice, left, right, or top, what you should be thinking is, Clark, you are telling me there's resonance. And that's exactly what I'm trying to tell you here. You could switch it in from the left-hand side, and that will give you octets throughout. But there are 3 different ways you could do that. You could have switched from the left, from the top, from the right. There are 3 different resonance structures here for carbonate. So take a second. What would be the bond order in carbonate for the carbon-oxygen bond? I would say that we have an averaging of the structure of a double bond and a single bond and a single bond. I see a total of 4 bonds around that carbon atom. 1, 2, 3, 4. 4 bonds being divided up in the 3 different directions. I think we're back to having a bond order of 4/3. This would be like what we had in nitrate, right? Within nitrate, we also had a bond order of 4/3. So this is another example of how we accommodated the resonance structures. We used that to come up with what the bond order was going to be. So in order to answer this question where it says compare the carbon-oxygen bonds, key first step that we want to do is we want to be able to come up with the bond order for each. Let's play that out now. How do we end up comparing them beyond simply the bond order for that? So first of all, I would say we saw in methanol, the bond order between the carbon and the oxygen was bond order of 1. That was in the Lewis structure. In carbon and oxygen, the bond order was 2. We had double bonds. And in carbonate, the bond order was 4/3. So one way I could compare the bonds would be in terms of bond order. That would be the first way I would begin to think about it. What if we wanted to compare it in terms of bond length? A single bond, that's our weakest bond, that is the longest bond. So I'd say in terms of bond length, methanol would be the longest, carbon dioxide would be the shortest. I'm using my insight about the bond order to now think about the bond length. Higher the bond order, closer together the atoms, the shorter the bond. Another comparison I can make might be, let's say in terms of bond enthalpy, the strength of the bond. My double bond is the strongest, my single bond is the weakest. So that's another comparison I could make. Another comparison I could make might be with a potential energy well diagram like this. This is one that I try to introduce this idea within the pre-class video here. This comes back to our description for the potential energy. Our reference value of 0 is when the particles are really far apart. As they've come closer together and there's an attraction, they go lower in potential energy. Now, if this was, let's say, the description in carbonate, this could be the description in CO2. What am I trying to depict there? I'm trying to say, okay, if the one on the left has a bond order of 4/3, what would be the bond order for the one on the right? I'm trying to draw it being a closer distance, it's more to the left there, and a lower potential energy. It's a deeper well. So that's another kind of comparison that I can make as well. So when I'm trying to do the comparisons here, really typical exam question. This says compare the bonds in these. And so a very typical exam question might be, rank these in terms of bond length, or rank these in terms of bond enthalpy, or it gives you different images and it tries to have, and you're asked to match them up. Different images with representations like this. All of those to me begin with, can I draw the Lewis structure and analyze to get the correct bond order? And if there's resonance, I need to account for that as well. That's a really good comprehensive question that brings together a lot of the topics within chapter 8. So when I looked at like some end of chapter questions, these were relevant for that. So this first one, 8.54, was looking at aspects of, well, do you have resonant structures or not? Could you compare the carbon-oxygen bond in this with the carbon-oxygen bonds in CO2? How do I make that prediction? I got to have the right Lewis structure. I got to have the right Lewis structure and get the bond order to make that comparison. 8.55, this is really similar to what we just worked through. This is really similar. The one that I just worked through was comparing methanol with CO2 with carbonate. This is comparing not methanol, but it puts carbon monoxide in there. So how would you do 8.55? You're going to have to draw the Lewis structures, determine the bond order, account for resonance if you need to, and we know there's resonance in carbonate. This last one right here, another really typical question. Based on the Lewis structures, predict the ordering from shortest to longest in these. There is no shortcut on this. For each of these, you have to first of all say, okay, I'm going to draw the Lewis structure. I'm going to get the bond order from that. And now I'm going to connect what I know about bond order with bond length. My cat's joining the conversation on this one. Okay. So to me, these are really good comprehensive questions at the end of chapter 8. Now, I mentioned the examples that we had that were hypervalent. Let's look at these two right here, okay? SF4, ClF4. So my first thought as I look at that is, I know that fluorine is going to be octets. I also know that sulfur and chlorine, I am not going to stress at all if those exceed an octet, because if I look at them, they're further down the periodic table, they're larger. I'm not going to get distressed at all if those exceed an octet. Here's the resulting Lewis structures for those. Notice in each of these cases for the fluorine atoms, We're completely seeing octets on all of those. If we look for each of these, then fluorine's always going to be an octet. And I'm not going to worry at all if sulfur and chlorine exceed an octet. How many do I see around chlorine here? 1, 2, 3, 4, 5, 6, 7, 8. I'm definitely over an octet here, but I'm not going to worry about that. Same thing with fluorine. I'm over an octet, but I'm not going to worry about it. Let's look at them though and see if their formal charges work. So for sulfur, it has 1, 2, 3, 4, 5, 6 different valence electrons. So if we were to calculate the formal charge for sulfur here, it would be 6 minus half of them that are found in bonds. So 6 minus 4 minus 2. 6 minus 4 minus 2. Sulfur has a formal charge of 0. Excellent. All of these have formal charges of 0, and I'm not going to worry that I exceeded an octet for sulfur. How about here for chlorine? Formal charge of 0 for the fluorines. For chlorine itself, 7 valence electrons. 7 minus 3 that are in bonds, 4 that are not in lone pairs. 7 minus 3 minus 4, formal charge of 0 for chlorine as well. So this was, again, very good Lewis structure, and I'm not going to worry that I exceed an octet. One more thought within here is if I need to draw these are actually pretty easy to draw and pretty easy to draw quickly, because you know right away that the fluorines, they're going to always be like this. They're never going to form a double bond. They're only going to form single bonds. Fluorines are most electronegative. It's only going to form single bonds for us. So in a sense, all I needed to do for my chlorine here is I need to say it has 1, 2, 3, 4, 5, 6, 7 valence electrons. Let me put those around there. 1, 2, 3, 4, 5, 6, 7. It's easy to draw for me these ones for the hypervalent. This idea of having those structures, these ones where we're going beyond with the hypervalent ones, we want to be able to predict the geometries for these. And that's what we do at the start of chapter 9. So people are making some really good comments and really good analysis here when we're trying to determine the geometry that we had using what is called Vesper theory. Let's get started on that with the start of chapter 9. Okay, I'm not going to complete the whole idea, but I want to get started on it for us. And then next class, we'll pick up there and continue on with more within chapter 9. So the first thought within here is when we draw our Lewis structures, they tell us about, well, do we have lone pairs present? Do we have single bonds, double bonds, triple bonds? How are things connected? That's what a Lewis structure tells us. They're not telling us the actual geometric arrangement. When I look at that picture there at the bottom, it looks like, oh, that looks like it's drawn to be 90 degrees. That's not what the artist is trying to represent. They're trying to show that carbon has 4 single bonds around it, but it is not trying to say that is a 90-degree angle. We need to work a little bit more to come up with what those angles actually are. So we want to think about this in 2 different ways. Around a given atom, we want to ask, how are the electrons arranged? That's what's called the electron domain geometry. And when I say electrons, they might be in bonds, they might be in lone pairs. So the electron domain geometry is looking at both bonds and lone pairs. Or we could ask just for, tell me about where the bonds are. That would lead us to the molecular geometry. So in a sense, the electron domain is telling us everything. The molecular is telling us a subset of that. We need to first think about the electron domain and see how does that influence what the molecular geometry is. So the examples that I had you work through, I chose some very simple molecules, simple being ones that I think we can draw them pretty quickly now. CH4, H2O, NH3, and BF3. So if we're drawing our Lewis structures for those, this would be my description for each. And again, the Lewis structure is not telling me the bond angles. It's just telling me how things are connected. Because if I look at H2O, as this is drawn, it sure looks like it's in a straight line, but that's not the case. We need to think about how we have the electron domain geometry and the molecular geometry and how those come together to tell us what the actual bond angles are. So as far as our learning objectives, you're going to need to know the names for the different geometries, whether we're talking about electron domain geometry or molecular. You need to be able to recognize and think about what the shapes are. And you need to be able to think about what are typical angles that you would find within that geometric structure. Now, as a resource, your book has images like this. This is one I grabbed from the e-text. Notice within the images here, it is showing you how you can think about the electron domain geometry, what the name of it is, the different numbers of bonding and non-bonding, and how that results in different molecular geometries. You know, as I looked at the tables within here, the only thing that's missing, it doesn't tell you what the angles are. So what I want to do now, I want to help us conceptually understand how are these tables constructed and how do we make sense of the angles that are involved? Because, you know, before when we would have this as a learning objective on our exams, you couldn't use any notes. We'd have you memorize what all of the different names for the geometries were, and we'd ask you about those. We can't do that anymore, all right? I mean, I'm not disappointed. We can't do that anymore because you could consult a table on this. So what I want to do is I want to empower you so that you understand what's going on with these particular tables. Because I think if I can do that, then you're going to really do well on these types of questions. And the one feature that I mentioned that's not included in that is the aspect of the angles. So let's see if we can understand how the tables are constructed, and let's add to these information about the angles. So in order to put these ideas together conceptually, we use what's called valence shell electron pair repulsion theory. It's a big acronym. We call it VSEPR, valence shell electron pair repulsion theory. So the idea here is that we're going to have a particular atom, and around it, what could be there? It could be a single bond or a higher order bond, like a double bond, or you could have non-bonding ones. Those are the different ways the electrons could be around a particular atom. And the arrangement that they adopt is going to be the one that minimizes the repulsion amongst these. If we're taking different electrons and putting them around the central atom, we want them to spread out as much as we can. Electrons repel other electrons. So we're going to choose a geometry that spaces everything out as much as possible. We're going to space out all of the different electron domains and then see what that means for the resulting molecular geometry. The electron domains are going to spread out as much as possible. And when I say electron domains, remember, that could be a bond or it could be a lone pair. That's what we have within this PhET sim here called molecule shapes, if you want to play with it. This is what I used to explore those ones that we had just a moment ago. The idea is that we can look at either the electron geometry or the molecular geometry. Here I see two bonds. I could add a third bond, a fourth bond. Notice how they all get spread out. This shape here is called a tetrahedral. The angles within an ideal tetrahedral are all 109.5. If I try to distort it and twist and turn it, it once again comes back so that all of them are as far apart from each other, and that's 109.5. That would have worked for CH4. How about for H2O? H2O has two bonds and two lone pairs. All four of those are spreading apart as much as they possibly can. What if I had three bonds in a lone pair? All of those are spreading apart as much as I possibly can. I can try to squish them together, but they keep spreading apart as much as they can. That's what VSEPR theory tells me. This last one right here, this is now to have 3 electron domains. 3 electron domains, all of them are bonds. 3 electron domains are adopting a shape that I call a trigonal planar. I don't call it that. That's what it is called. Okay, that geometry is a trigonal planar. It's called planar because they're all flat within the same plane. Trigonal because you've got 3. The internal angles on that are all 120, 120, 120. They add up, if you think about your geometry, they add up to 360 degrees, 120, 120, 120 in that trigonal planar geometry. So within that simulation right there, if we think about the electron geometry, CH4 was a tetrahedral with 4 bonds. H2O was a tetrahedral with 2 bonds and 2 lone pairs. NH3 was a tetrahedral with 3 bonds and lone pair. If you have 4 different electron domains, it's tetrahedral. But notice how the geometries were different, because when we're the molecular geometry, because when we're looking at the molecular geometry, we're only talking about where the atoms are found. The electron domain geometry affected the molecular geometry. Couple angles then that I said we want to be aware of. In an ideal tetrahedral, meaning you've got all 4 directions the same, it turns out that angle is 109.5. So I want you to know that that one, the ideal angles in a tetrahedral are all 109.5. We also looked at the ideal ones here for a trigonal planar. The ideal angles in that are all 120, 120, 120. They're not shown in this picture. They're not 90 degrees and 180 degrees. They're 120, 120, 120 in this trigonal planar one. Those are our ideal geometries. So if we go back, this is a image from the e-text. Notice what this is telling us. It's telling us if you have a combination of bonding domains and non-bonding. Bonding are the bonds, non-bonding are the lone pairs. What would be the resulting geometry? That's how we are looking at those different ones to see what the resulting shape is. And to add to that, I think we have some insights about the angles too. If it's a linear one, it's 180 degrees. Trigonal planar, they're all 120. 120, 120, 120. Tetrahedral, in my ideal case, they're all 109.5. So let's look at this one. So how would we begin to think about something like a molecule like CO2CO? What would be the VSEPR predicted geometry here? It begins with drawing the Lewis structure. So here's our Lewis structure for that. Octets for everything. In this case, the electron domain geometry and the molecular geometry, they're the same. If you don't have any lone pairs on that central atom, they're going to be the same. Both the electron domain geometry and the molecular ones, in this case, they're both trigonal planar. The idea of having the electron domain geometry and the molecular one different, that's when you have lone pairs present. In this case, we see that they're all tetrahedral when we're thinking about the electron domains. But when they're a molecular one, we're only looking at the bonds. They're trying to show that at the bottom here, where they're saying, let's start with this tetrahedral. You could have all 4 bonds, or if you remove one of those and make it a lone pair there, that's a trigonal pyramid. If you have 2 sets of lone pairs, that makes it bent. That's what's matching up for the CH4, the NH3, or the bent geometry. Now notice what else is going on. I had the ideal geometry, the tetrahedral, where they're all equivalent bonds, and I said that was an angle of 109.5. In this one, notice what happened. The bond angle has gotten a little bit smaller. I'm going to interpret that because I'm going to say the lone pair is taking up more space and it's sort of squishing together the other part of the molecule. And in the bent one, even more so. We're going to see slight deviations from the ideal geometry when lone pairs are present. A lone pair takes up more space than a bond. It's leading to a slight decrease from that ideal arrangement. You are not going to need to know, oh, is it 107 degrees or 106 degrees? But I do want you to know that it is a slightly smaller value than the ideal value. A lone pair takes up more space, so it's leading to a slightly smaller bond angle because the lone pair is taking up more. You don't need to know the specific value, but you need to know that deviation from the ideal behavior. So if I look back at this chart now, I've mentioned that the bond angles for a linear, it's 120, trigonal planar, it's 180, Trigonoplanar, they're all 120. The ideotetrahedral, they're all 109.5. Now, if I look at these other ones, I think within this bent structure, because I have lone pair there, it would be a little bit smaller than 120. Trigonal pyramid, little bit smaller. Bent, little bit smaller. They're all a little bit smaller than the ideogeometry. In the bent one here, it would be a case where it would be a little bit smaller than 120. In this bottom case right here, I think it would be a little bit smaller than 109.5. In both cases, I'm first thinking about what is the ideal bond angle, okay? And then what would be a deviation from that? We don't need an exact value, but I think we get a really good sense of how they compare. Now, we've compared then, what takes up more space, a single bond or a lone pair? A lone pair takes up more space. How about a single bond or a double bond? So if we go back to this one, let's add some experimental data to it. These are the actual bond angles. Experimentally, if you use something like X-ray diffraction, you could determine the placement of the atoms. These would be the actual bond angles. So initially, if these were all equivalent, I would have said it was 120, 120, 120. But notice what happens. It looks like this part is now taking up more space. It's squishing the chlorine, carbon, chlorine smaller than 120. And these are becoming a little bigger than 120. It still adds up to 360 all the way around. Once again, you don't need to know that specific value, but I think we've added more information here. We've seen that a double bond takes up more space than a single bond, and it's squishing this part of the molecule a little bit more close together. This idea of thinking about, well, what would be the initial ideal arrangement? And then how do we modify that? That's an important skill for us. Okay. Now, let me throw this one at you. So I'm back to my friend here, the nitrate anion. What do you think the oxygen nitrogen angles are in nitrate? Would you say they're all exactly 120? Or would you say, no, I've got maybe 125, 125, 110. What do you think for nitrate here? Can you take about 10 more seconds? Okay, so I'm glad I asked this question here. So we got a strong consensus that you don't have all 120, 120, 120. You might have two of them that are a little bit larger and one a little bit smaller. So if I can get in your head on that, what you're doing is you're saying, okay, we just said a double bond takes up more space. I see a double bond there. I think that this angle would be bigger, this angle would be bigger, and it's squishing together a little bit, this oxygen, nitrogen, oxygen. I completely follow your logic on that. And I'm going to disagree. I'm going to say that they are all precisely 120. And if you say, what the hell just happened? I'm going to say, let's remember we have resonance structures here. With resonance, we do not have a double bond, a single bond, and a single bond. We have an averaging of those. Remember, we said this was a case where the bond order was 4/3. Another feature that would be averaged would be the fact that you don't have a double bond, a single, and a single. It's going to go back, and they're all going to be equivalent to each other. So it comes out being all 120, 120, 120. So within this one, this is another feature in a way that I would say proves resonance being right. It proves resonance because the nitrogen oxygen bond distances in nitrate, they're all the same. And all of the angles are the same too. So this is more evidence that you don't have a double bond and a single bond. So another thing that resonance does, it averages the bond length. And if you're making them all the same within here, it's also leading to all of the angles being equivalent. Tricky question, but I'd say this is more evidence that resonance is applicable here. Now, this case, this was one that I had within the pre-class one. I saw a lot of thoughtful work and analysis on this. Let me sort of offer more of an explanation on this. A lot's going on within these different parts. I'm calling this molecular geometry and bond angles. The task at hand is, can we estimate what these different bond angles are and which one would be closest to 109.5? So a lot of ones, a key question people had on this, a key main one was, do we need to know a specific value? We do not need to know a specific value. I don't know a specific value. I can tell you if they're how they compare with an ideal value. You don't need a specific number. We just want to get approximate numbers, okay? So we don't need a specific one, but we want to be able to come up with a good general idea. Within our analysis for this, let's say we're looking here at the angles around this oxygen atom. The way that we want to do it is we want to focus right on that oxygen atom. We want to say, okay, I don't need to worry about anything else. Let me just look at that particular atom. Around this particular atom, I see 4 electron domains. Bond, bond, lone pair, lone pair. That tells me that this is a tetrahedral electron domain geometry. I see 2 of them are bonding. That is going to be a bent molecular geometry. It's bent just like I would see in water. The lone pairs are going to take up a little bit more space than the bonds. So instead of this ideal angle of 109.5, that internal angle, it's going to be a little bit smaller. Maybe it's 108. Maybe it's 106. It's a little bit smaller than 109.5. Notice what I did within my analysis. I'm just looking at the most immediate vicinity there. I'm not worrying about other structural features. I'm going to say that the bond angles are going to be due to that immediate vicinity. And that comes up and says, oh, it's going to be a little bit smaller than a tetrahedral then. If I look at this next one, I would do exactly the same thing. If I zoom in on that, I'm not going to worry about any of the broader picture. I'm going to look at this and say, okay, I see 3 electron domains. 3 electron domains means it's a trigonoplanar electron domain geometry. All of them are bonding. So it's a trigonoplanar molecular geometry. However, one of them is a double bond. That's going to take up a little bit more space. So instead of all being 120, 120, 120, this part's going to be a little bit bigger. Maybe it's 122. Maybe 123, 124. It's going to be a little bit bigger. I don't need to know the specific value, but I know it's going to be a little bigger than the 120. That's how I would analyze these. I would say that I have examples of 4 electron domains, which would be tetrahedral. Examples of trigonal ones. These right here just have 2 electron domains. It's going to be in a straight line. And then I would revisit and say, okay, now with those electron domains, are they single bonds? Are they lone pairs? What do I take away from those? That's how I come up with these particular values. That's how I'm coming up. And, I'm trying to say it's about that particular value. The one that I think I'm most confident in that it would have a value of around 109.5 is this one right here. Because I see 4 electron domains. They're all bonds. My ideal tetrahedral has a value of 109.5. I think that's going to be my best example of one that's closest to 109.5. Now, I know this is one that I tried to explain a little bit and introduce in the pre-class video. There was a lot of questions on it. And I'm trying to sort of revisit that same one. So I'm curious within here. In the chat, tell me, is there one of these that you want to learn more about? Okay. Is there one of these that you want a fuller explanation? And I can try a little bit more. Okay. So as these are coming in, it tells me that it would be beneficial to talk about all of them. Okay. So let me step through these. Let me share my reasoning once again. So around this first atom right here, around this, the angle that I'm interested in, the bond angle, we call them the internal angles. They're like the shorter angle. It's the angle between hydrogen, oxygen, and carbon. That internal angle there. That particular geometry, I see that I had 2 lone pairs and 2 bonds around it. Even though it's being drawn in a straight line, it's not a straight line at all. It's a bent geometry because it's initially a tetrahedral with 2 sets of lone pairs and 2 bonds. Those are 4 electron domains. The lone pairs are taking up a little bit more space. So instead of having the ideal bond angle of 109.5, the lone pairs take up a little bit more space, and it squishes that hydrogen, oxygen, carbon bond a little bit smaller. How much smaller? Well, instead of being 109.5, it's going to be a number a little bit smaller than that. Just like we saw in NH3 and in H2O, in both of those cases, we had a tetrahedral electron domain geometry, and the molecular was a little bit smaller because the lone pairs were taking up more space. It's not drawn that way, but that is exactly what this means. It means that you have 2 different lone pairs and 2 bonds, and the lone pairs are going to take up a little bit more space. The idea of taking up a little bit more space, that's what's taking place within this one right here too. Around this carbon, I see that I have 1, 2, 3 different electron domains. I would say if all of those were equivalent, let's say all single bonds, I'd say it'd be 120, 120, 120. It wouldn't be drawn like this. It wouldn't be 90 degrees. This isn't trying to show 90 degrees. This is just showing how they're connected. I think this would be 120, 120, 120 if they were all single bonds. But the double bond takes up a little bit more space. The double bond takes up a little bit more space, and it's squishing this carbon, this hydrogen, carbon, hydrogen one, a little bit closer together. This angle is getting a little bit larger. This angle is getting a little bit smaller. That's how I make sense for angles both 2 and 3. For angles 5 and 6, in this case, the image is right. The image is right because this is just a straight line. In order to separate things as much as I can, it puts it in a straight line. There are no lone pairs disturbing that or altering it. Straight line is as far apart as I can possibly get. That's why it's 180 degrees. It's exactly in a straight line, exactly in a straight line. And then back to the 109.5, my reading on this, I'm classifying that as a tetrahedral for the electron domain. I'm classifying it as a tetrahedral for the molecular domain. And I'd say this is pretty close to being an ideal arrangement because they're all single bonds, which means 109.5. Now, I know within here, as I'm talking about it, and I'm trying to rationalize these, one thing that occurs to me is I've mentioned, hey, you can look at the particular tables. You can use that as, to give you additional insight. But at least for me, I've really internalized what these geometries are. I really take this image right here and I take it off the piece of paper, and I can really visualize it like within that simulation. And the reason I'm saying that is I think that if you can't visualize it and take it off the piece of paper, you're going to really struggle with a question like this. Looking back at a table of some kind, I think at least with me, it would be really tough to try to make sense of what's going on. I think what you have to do is you have to say, okay, I can visualize and make sense of the information in that table. Not, oh, well, let me look it up in the table. I think you really got to be able to try to take it into a 3D structure and begin to visualize it that way. Because if you gave me this question right here, and I didn't have these representations in my mind of what it looks like as a 3D shape, I would really struggle looking up at that table and trying to make sense of it. So I guess what I'm recommending is, I don't think I would be satisfied by saying I can look up information in that table. I think an even better one is, I mentioned the PhET sim for this, the molecule shape one. Great resource might be, okay, let me explore each of those shapes with that PhET sim. Let me try to visualize what's going on. I think if you can do that, then I think you're in really good shape. One feature I want to bring up on this one that I know that some students were sort of asking about. Remember when I was trying to determine the geometries and stuff here, I looked at just the most local environment. I wasn't looking at things further away. When you're trying to do your ranking or your analysis, just look at the most local environment, classified in terms of what its electron domain geometry is. Don't be looking more broadly about the rest of the molecule. That is not going to be important. The bond angles are going to be determined by that most immediate vicinity. So in here, we've been spending some time on how VSEPR geometry can be used if we're thinking about 2 electron domains, which makes it linear, 3 electron domains, which are trigonoplanar, or 4, which make it tetrahedral. And we have examples then of corresponding shapes if they're all bonds or if we have a combination of bonds and lone pairs. For all of these, our strategy needs to be, we need to be able to first draw the Lewis structure, apply VSEPR, and be able to think about what the electron domain geometry is and the molecular geometry. We'd want to be able to name what the geometry is and think about then the bond angles. Estimate those in order to do rankings and comparisons. Another skill that we can do within that is we can determine whether the molecule is polar or not. That was something that was presented in the pre-class video, but I want to include that in our next class. I intentionally want to sort of overlap that. Our plan here for what our next class is as it pertains to these ideas. We've got 2 different things that we want to wrap up pertaining to VSEPR. The molecular shapes that we've talked about tonight, they only went up to a tetrahedral for the electron domain geometry. We're going to go beyond that. We're going to look at the ones that are beyond an octet that we called hypervalent. So we're going to look at those particular geometries and make sense of those next time. There's tables describing that. There's a PhET sim that we can explore with that. So we're going to look at shapes that go beyond a tetrahedral next time. We're also going to be looking at applications involving polarity. Based on the shape, is it a polar molecule or a non-polar molecule? That's going to be the first half of class. Second half of class, we're going to move on to a bonding model called valence bond theory. Valence bond theory, if you've heard of hybridized orbitals before, those are what are included in valence bond theory. The remainder of chapter 9, we have 2 different bonding approaches that we're going to look at. Valence bond theory and what's called molecular orbital theory. Both of those, I think, are 2 really exciting ideas that we have. And if by exciting, I mean, they're some of the more complex ideas we have, it's true, okay? The next week and a half, we've got, I would say, the most complex ideas that we're going to have this entire semester. You can do them, okay? You can absolutely do them, but I'm just putting my cards on the table. I know that the second half of chapter 9 are some of the most challenging and far-reaching ideas that we're going to have. A key thing that I wanted to take away from the ideas that we had here, I give a few suggested problems. So the ones here at the top, we're looking at different aspects of the molecule structure. Trigonoplanar, tetrahedral, and linear are all ones that we discussed. And the question is, well, what kind of bond angles would you find in those? In 9.23, you're asked to consider electron domain and molecular geometries. I think we've only just started that because several of these are corresponding to hypervalent ones that we're going to talk about next time. This bottom part right here, give the electron domain and molecular geometry. What I'd like you to do within those, if you want to give them a try, do the ones that work up to having a tetrahedral electron domain. If you have to go beyond that, that's an idea that we're going to add next time. I know for some of these, though, draw the Lewis structure. If the Lewis structure is not hypervalent, I think you'll be able to do it. A key thing that we did practice tonight, though, is this question right here. Notice the format. Give the approximate values for these bond angles. This is what I was trying to practice as we were finishing class. This is a skill that I think that we covered. Give this one a try, please. This question right here, this is really similar to what I've seen on exams. What I've seen on exams would be an image just like A right here. And it would say, okay, tell me information about these bond angles. Which one's greater? Is 1 or 2 greater? Are they equal to each other? Compare the bond angles in A and D, stuff like that. These kind of ideas of taking the image and be able to come up with approximate values, I'm sure you're going to have an exam question like that. And this is something that we did practice. Give that a try. And if you have questions about that, shoot me a message. I'll be really happy to help you on any of these. And let's build up from here. And with that, I'm going to say enough for tonight. Once again, great job. I'll hang around if you got questions.
Hi, Dr. Clark. I have a question.
Hey. Yeah.
Can you go back to the slide with the, it had all the various bond angles of some organic molecule. Yep. And I was wondering why the triple bonded carbon, yeah, this is the one, why 180 would be the angle and not something smaller.
Yeah, I'm pretty much, I know what your reasoning is, but explain your thinking to me.
So, yeah, I'm thinking that triple bond would, I guess, take up more space in your words.
Yep.
And it would create slightly less of a 180 angle on one side.
Okay, so what I'd like you to do right now is physically do this for me, okay? Put your arms out so one goes straight to the left and one goes straight to the right.
Okay.
Okay, now with your right hand, make it so your hand opens up so it's like taking up even more space.
Okay.
Okay, so what is the angle between that and your other arm? The farthest it can be apart is 180. Yeah. If it becomes 175, that's getting closer together. I completely get, but in this case, linear, it can't get any closer together. So I agree with you. A triple bond would take up more, but the absolute largest separation, it's got to stay at 180.
Okay, that makes sense.
Mm-hmm.
I actually have another question as well about resonance.
Mm-hmm.
So in nature, would it be the case that in the case of nitrate, all 3 possible Lewis structures can occur, and that on average, it just so happens that the bond angles are 120 because of the average.
Mm-hmm. I think the way we have to think about it is, okay, these Lewis structures, they were an initial way that we could begin to think about how the molecule was constructed. But what we are finding is there are examples where a single Lewis structure is insufficient. It is not actually helping us describe what we find experimentally. It's a shortcoming of the Lewis structure itself. It's a very simple way to describe what's there, but it doesn't really capture what's there. We can't really just have we can't really have single bonds and double bonds, because that's not really describing what the corresponding angles would be or distances. So in a way, it's saying our tool of drawing the Lewis structure, that Lewis structure was a simple approach, but it's really not capturing what's going on there. So instead of trying to say, oh, well, I think maybe the Lewis structure is sort of right, I think what it's saying is a single Lewis structure does not capture what's really going on. It's not consistent with what the experimental value is. We are really having to say it's not a Lewis structure is sufficient. We end up having sort of this combination of Lewis structures. That's our way of thinking about it. So I would say in some ways it shows more about the shortcoming of drawing Lewis structures because they're not consistent with what nature actually gives us.
Okay. So double bonds, they don't actually, in the case of resonance, they don't actually occur. It's more like 1.5.
You got it.
Okay.
Yep, you got it. And
Or one-
sometimes what I see is instead of drawing like a double and a single, sometimes you'll see they just draw them like at dash lines because they want to say, hey, it's really not a double and a single. It's that combination.
Hmm.
So we don't really have doubles and singles anymore. We just have this new combination in between.
I see. In the case of resonance,
Correct.
You say there are double bonds in molecules with only one Lewis structure?
Yeah, I would say in these cases, on the screen, I think I have a combination of single, double, and triple bonds. I think all of these, what I see is what I get. But I think when I have resonance, the Lewis structures are not really describing what takes place.
Okay. That makes sense. Thank you.
Yep.
Mr. Clark.
Mhm.
What would be the bonding